Let's look at a proof of the fundamental theorem of calculus, part 1. First, let's read the theorem again. If f is a continuous function on the closed interval from a to b, then the function g, defined by g of x equals the integral from a to x of f of t dt, is continuous on the closed interval from a to b and differentiable on the open interval from a to b, and g prime of x equals f of x. So we've got assumption of continuous on the closed interval, and that this g of x is defined as so, and then we need to show that it's continuous and that g prime of x equals f of x. So let's start by looking at this picture that we had before. We're looking from a to b, and we're looking at an area x, x plus h. So if we have g of x plus h minus g of x, by the definition of g above here, that would be the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. Now, by the additivity of integrals, if we have the integral from a to x plus h, that would equal the integral from a to x plus the integral from x to x plus h. So we're going to replace this with that integral from a to x of f of t dt plus the integral from x to x plus h of f of t dt, and then we still have this minus this integral on the end, a to x of f of t dt. Now these will cancel, and so what we started with, g of x plus h minus g of x equals the integral from x to x plus h of f of t dt. Now we're going to do one last thing. We are going to take h positive, and a similar proof can be done for h negative, but for h positive we are going to divide both sides by h. Now let's keep this result in mind because we're going to come back and use it in a minute. Now let's look at the function f of x, and if we look between x and x plus h, since f is a continuous function, we know by the extreme value theorem that somewhere on the closed interval from x to x plus h, it takes on its maximum and minimum. So it has an absolute minimum. We're going to say that occurs at a place we'll call u, and it has an absolute maximum, and that's going to occur at v. Now if we looked at the integral from x to x plus h of f of t dt, by properties of integrals, we know that that's going to be greater than or equal to a rectangle that we make that is little m, its minimum high, and h wide. So that would be mh, and we know that integral is going to be less than or equal to a rectangle that we make that is capital M, the maximum high, and still has that width of h. Since h was positive, divide everything by h. What I have left, well, this looks familiar. This is exactly what we had right here. So we could replace that with g of x minus g of x over h. So we're going to do that. G of x plus h minus g of x over h, and that's going to be greater than or equal to little m. But as we look, little m is nothing more than the function value at u. So let's express that as the function at u, and that's going to be less than or equal to capital M, which is the function value at v. Now let's look at the limit as h approaches 0 of the function at u. As we look at this picture, we see that as h approaches 0, then u is going to get closer and closer and closer to x. So this would equal the limit as u approaches x of f of u, but then we can directly evaluate that, so that's going to equal f of x. Let's now look at the limit as h approaches 0 of f of v, and if we're looking at v and we're looking as h is approaching 0, we see that v is also going to approach x. So that's going to be the limit as v approaches x of f of v, and so that's also going to equal f of x. Now, looking at this inequality, we have the limit as h approaches 0 of this left-hand side is f of x, and we have the limit as h approaches 0 of this right-hand side is also f of x. So by the squeeze theorem, we have the limit as h approaches 0 of g of x plus h minus g of x over h is also f of x. But wait a minute, let's look at this. That looks familiar. That is just the limit definition of the derivative of g. So therefore, we have now proven that g prime of x equals f of x. Let's look at the idea then of continuity. So if we had x equaling a, then we would have g prime of a would equal the limit as h approaches 0 of g of a plus h minus g of a all over h, but we know that limit equals f of a. And similarly, g prime of b equals the limit as h approaches 0 of g of b plus h minus g of b all over h, but we know that equals f of b. So we have the limit equaling the function values for a to b, because we could have any a and any b here, so we're looking at our closed interval from a to b. The function is then continuous from a to b. So we now have established that if f was continuous from a to b, and if we also know that g of x equals this integral, then g is continuous on the closed interval from a to b, and it's differentiable, and its derivative equals f of x.